Welcome to Deep Notes. You're entering a restricted space dedicated to signal, not noise. I'm Nina, and in this session, we're not just defining a term, we're establishing a mindset, the architect's view of algorithms. This is the foundation. It's the bedrock upon which all robust data systems are built.
So let's start with a question you've probably asked yourself. Why does the exact same task take 5 seconds on one system, but 5 hours on another? Now, let me be very clear. This is not a hardware problem. It's a logic problem. For a data professional, understanding the answer is what separates a functional system from a catastrophic failure. The difference is the design, the blueprint, the algorithm you choose. Getting this right is absolutely not optional. You know, the word algorithm gets thrown around a lot. It's often treated like some kind of black box, this mystical thing that controls our systems. That's just wrong. An algorithm isn't magic. It's a recipe. So let's dismantle that abstraction and really expose the mechanics underneath. Let's just decode this formal definition for a second. Explicit and unambiguous mean there is zero room for interpretation. Mechanically executable means a machine can follow the steps without any creative thought. It's pure instruction. It's a totally deterministic process that takes you from an input to an output.
Think about this. This is an algorithm. It's just a simple loop, right? It's got a clear start, it has repeatable steps, and it has a defined end. The logic is completely transparent. And honestly, if you understand this, you understand the fundamental structure of all algorithms. The complexity doesn't come from the concept itself. It comes from the problem you're trying to solve.
Okay, so if all algorithms are just recipes, does that mean they're all equal? Absolutely not. Some recipes are efficient, others will burn down your entire kitchen. And in systems architecture, the kitchen is your server, your budget, your deadline. We have to measure the cost before we execute.
We measure cost in terms of how it scales with the size of your data. Linear cost, that's manageable. If you double the data, you roughly double the processing time. Makes sense. But quadratic cost, that's a trap. You double the data and you quadruple the time. This is the signature of a system that will not scale, period.
Our 99 bottles algorithm, that has a linear cost. To sing about 100 bottles takes about twice as long as singing about 50. The work scales directly with N, the number of bottles. This is efficient. This is a design we can actually trust.
Now, on the other hand, think about the 12 days of Christmas. Every day, you have to repeat all the gifts from the previous days. You see that? This nested structure, a loop inside of another loop, is a massive red flag for quadratic cost. The work doesn't just add up, it multiplies. And for a data architect who's handling real-world data, the consequences of this are what really matter. With a small input, the difference between linear and quadratic is just a few seconds. But with a massive data set, it's the difference between a successful query and a system that effectively crashes. An inefficient algorithm is basically a denial of service attack you commit against yourself. So how do we avoid this quadratic trap when we're faced with a really complex problem? We have to adopt a new mental model. We don't try to solve the whole problem all at once. We simplify and we delegate. And this is the principle of recursion. Look, this isn't some new idea in computer science. This is a timeless strategy for managing complexity. You break a huge, unmanageable problem into smaller, identical, and far more manageable pieces.
This right here is the core of the recursive mindset. The source material calls it the recursion fairy, which I kind of like. As an architect, your job is to do just one thing: make the problem smaller. You then hand that smaller problem to a black box. That's the recursive call, and you just trust that it's going to return the correct result. You don't need to trace every single step. You just need to trust the protocol.
All right, let's move from theory to execution. We're now going to architect a solution for a really common data problem, sorting, using this exact divide and conquer strategy.
So here's our system input, a completely unsorted array of data. Our task is to design an efficient, scalable sorting algorithm. The first step is almost trivial. We do no real work here. We just divide the problem into 2 smaller, independent subproblems. That's it. The problem has now been simplified. Now we delegate. We hand these 2 smaller arrays to our recursion fairy. We're not going to worry about how it sorts them. We just treat it like a black box and assume the recursive call works. By the time we get control back, boom, the subproblems are solved. And this is the final step, the conquer phase. The real work is here, but now it's a simple task. We take the two, now sorted, sub-arrays, and we efficiently merge them into a single, final, sorted array. And that merge operation, it's linear.
So why is this design so much better? Just look at the structure. At each level of the recursion, we do a simple, linear amount of work to merge the pieces. But because we cut the problem in half each time, we don't have to do this that many times. This combination of doing a little bit of work but only a few times is incredibly efficient. It's so much more scalable than a quadratic solution that just multiplies its own work.
So you see, we've moved from looking at an algorithm as some mysterious black box to understanding it as a blueprint that we design and we control. You define the recipe, you analyze its cost, and you use recursive thinking to build systems that actually scale with complexity. This is your roadmap. Trust the logic. Build the system.